Welcome back, everyone, to MAE170. This is lecture 5 in week number 3. Last time we saw the concept of the final value for a function when a final value exists. Remember that also the final value can be called steady state value, and how to compute it in both the time domain, that is taking the limit for t that goes to infinity of the function in the time domain, but also in the S domain, applying the final value theorem. And in the S domain, the final value is computed taking the limit for S that goes to 0 of S times the function in the S domain. However, you always have to remember to check the conditions for the applicability of the final value theorem. And summarizing the two conditions, you have to compute the poles of a function and take a look at the real part of these poles. If all the poles have negative real part, then you can apply the final value theorem. You can have at most one pole that is equal to 0. But if you have poles on the imaginary axis or on the right hand side of the complex plane, then the final value theorem cannot be applied anymore because the function does not have a final value. It might be oscillating forever like a harmonic function, or it might go to infinity as time goes to infinity. So always check the poles of the function whose final value you want to compute. Then we saw the error analysis and the concept of system types. We matched certain system types number with certain known inputs, and we found that the steady state error could be either 0, a finite value, or infinity. In this lecture, we're going to take a look at second order systems, and everything I will be talking about is in chapter 5 of your textbook. All right, before tackling second order system, we have to understand how we defined the number of the order of a system. Well, that's pretty easy because the order of the system coincides with the number of poles of the system's transfer function. So if we have a certain system described by the transfer function g of s, for instance, and let's say that this g of s is s plus 2 over s squared plus 4s, s cubed plus 4s squared plus 9s plus 3. The number of poles are the roots of the denominator when equated to 0. And since the denominator is a polynomial of the third degree, then we are going to have 3 poles. So number of poles is equal to 3. And therefore, this describes a third order system. Now, something to be aware of is that the order of a system is not necessarily equal to its type. From what we saw last time, the system type number is the number of poles equal to 0, so the poles at the origin, of the open loop transfer function. And it really makes sense only when we consider the closed loop systems. So in other words, when we want to study a closed loop system and we're closing the loop around a certain system described by the transfer function L of S, also known as open loop transfer function or loop transfer function, then the system type number is the number of poles of L of S at the origin, or in other words, poles that are exactly equal to 0. So once again, the order of a system does not necessarily coincide with the system type number. Those are two different things. Keep that in mind. All right, so we're going to focus our attention today on second order systems. So in other words, we are considering systems whose transfer function's denominator is a polynomial of order 2 or degree 2. So in this case, as usual, we have our input, our system described by the transfer function g of s, and then we're going to have our output modified by the system. So the system transfer function can be written as usual as a numerator over a denominator. And for a second order system, and I've already anticipated that a couple of lectures ago, we can write it as omega n squared over s squared plus 2 zeta omega n s plus omega n squared. And we've also given names to these parameters. In particular, we have omega n, which is a positive number, and that is known as a natural frequency, whereas zeta can be equal to 0 or greater than 0 and is known as the damping ratio. Now, how many poles do we have for the transfer function g of s? As usual, we need to solve d of s equals 0, because the roots of such equation are the poles of the transfer function. So d of s equals 0 is also known as the characteristic equation of a transfer function. And sometimes we're going to find it with delta of s equals 0. So delta, capital delta, symbolizes the characteristic equation. So d of s equals 0 or delta of s equals 0 are usually the same thing, and they're referred to the characteristic equation. So in this case, we have that this is equal to s squared plus 2 zeta omega n s plus omega n squared equals 0. All right, so now we have to find the roots of these equations, that is the poles. Of course, here the result or the poles will depend on the values of the two parameters, zeta and omega n. We're going to do the following. We're going to follow, or we're going to solve equation 1 for different values of the damping ratio zeta. We're going to consider 4 cases. Case number 1, when zeta is equal to 0. So this is also known as the undamped case. So there's no damping. And then we're going to consider the case in which zeta is between 0 and 1. And this is known as the underdamped case. Then case number 3 is when zeta is exactly equal to 1, and this is known as the critically damped case. And finally, when zeta is greater than 1, we're going to have the so-called overdamped systems. All right, let's start from case number 1. When zeta is equal to 0, the characteristic equations reduces to s squared plus omega n squared equals 0. It's quite straightforward. So what are the poles? Well, we're going to have P1 and P2. There's going to be equal to plus I omega n and minus I omega n. In other words, the poles are purely imaginary numbers. They don't have a real part, or the real part is equal to 0, and they are complex conjugate. So their imaginary part is equal but opposite. Case 2. What if the damping ratio is between 0 and 1? Well, in this case, we have the whole equation. We maintain the second term. And just take a look that this is simply a quadratic equation. So normally we would have as squared plus bs plus c equals 0. So A is equal to 1, B is equal to 2 zeta omega n, and C is equal to omega n squared. All right, so the solutions P1 and 2 are equal to minus B over 2A plus or minus 1 over 2A square root of B squared minus 4AC. So in this case, we're going to have that minus B is minus zeta omega n, well, times 2 over 2A, A is equal to 1. So we simply have minus zeta times omega n plus or minus 1/2. And then we have 4 zeta squared omega n squared minus 4 omega n squared. We're going to take the 4 omega n squared and bring it outside the square root. So we're left with minus zeta omega n plus or minus omega n. And inside, we're left with zeta squared minus 1. Since zeta is between 0 and 1, zeta squared is going to also be between 0 and 1. And so if we subtract 1 to a number that is between 0 and 1, we're going to find a negative number. So whatever we have, the argument of this square root is negative. Therefore, we're going to end up with complex conjugate numbers when it comes to the poles. So the poles are actually minus zeta omega n plus or minus I omega n. And now we have to invert the order. So it's going to be 1 minus zeta squared. So to recap, P1 is minus zeta omega n plus I omega n square root of 1 minus zeta squared, and P2 is very similar, but we have a minus sign. So in this case, you see that whenever we have a damping ratio that is greater than 0, we went from having purely imaginary poles to complex conjugate poles, because now these two poles have a real part that is different than 0. Okay, now let's go to case number 3. So for case number 3, we have that zeta is exactly equal to 1. So our characteristic equation reduces to s squared plus 2 omega n s plus omega n squared equals 0. And this is a perfect square, that is s plus omega n all squared equals 0. So in this case, the roots of such characteristic equations, that is the poles, are equal. They're always 2, but they are the same. So P1 is equal to minus omega n, and P2 is also equal to minus omega n. So they are repeated, but you see that now they are real poles. Or you can say there's one pole, one real pole, negative real pole, with multiplicity equal 2. Finally, if we have a damping ratio that is greater than 1, that is, if we are considering an overdamped system, then once again, we have the full expression for the characteristic equation. This time, though, the argument, so it's equivalent to this case here, but now the argument of the square root is going to be positive. So the two roots are real, and they're going to be equal to minus zeta omega n plus or minus omega n square root of zeta squared minus 1. you see that zeta squared minus 1 now is positive because zeta is greater than 1. So in this case, both P1 and P2 are real numbers. So we have real and distinct poles. And well, you can also prove, and I wrote it down in the notes, but I'll let you verify that both P1 and P2 are negative numbers. So both P1 and P2 are negative if zeta is greater than 1 and omega n is greater than 0. It's quite easy to see, especially for P1. All right, so now why don't we visualize all these poles for these 4 cases in the S-plane? Remember the S-plane, we can plot complex numbers in a plane, and the coordinates are going to be their real part and their imaginary part. So the x-axis is the real axis, and the y-axis is the imaginary axis. So starting from the undamped case, we have the 2 poles were equal to plus or minus I omega n. And you see that these 2 poles lie exactly on the imaginary axis. However, if we increase slightly the damping ratio, the underdamped poles are going to lie on a semicircle of radius omega n. And let's prove that that is indeed the case. If you go back to the expression for P1 and P2 in the underdamped case, you see that the real part is the same. So that is equal to minus zeta omega n. So let's write it down. This is minus zeta omega n, or, you know, if you just want the distance, it would be the absolute value of that. And the y component, or the y coordinate, is instead, so in other words, this distance is omega n square root of 1 minus sigma squared. So what is the length of this arrow here? So that is, what is the distance between the underdamped complex pole and the origin of the S-plane? Well, that is, we can use Pythagoras theorem, and we have omega zeta squared omega n squared plus omega n squared times 1 minus zeta squared, everything under the square root, and this is the length of the arrow. And so we have that this goes away with this. So we're left with omega n, absolute value of omega n, but since omega n is positive, this is simply equal to omega n. So the length is omega n. That's why, as I said, the poles can be anywhere on this semicircle of radius omega n. Now, the exact location of the poles depend on the damping ratio zeta. If we have a lower damping ratio, we're going to be closer to the imaginary axis. If we have a higher damping ratio, then we're going to be closer to the real axis. So if we increase the damping ratio, we're gonna slide down the semicircle towards the real axis. And in fact, when we have the critically damped poles, they both coincide at minus omega n. And this is valid for zeta equals 1. So you see that we started from the imaginary axis for zeta equals 0. As we increased the damping ratio, we started going towards the real axis, always on the semicircle of radius omega n, until we hit the real axis at minus omega n. Now, if we increase even further the damping ratio, what's going to happen is that we have to diverge. And if you remember, in the fourth case, that is the overdamped case, the two poles were both real and negative. So what happens is that we're going to have, for instance, a pole here and a pole over here, or maybe a pole here and a pole over here. So as we increase further the damping ratio, we're moving now on the real axis to the left and to the right. In the extreme case of zeta, that is the damping ratio going all the way to infinity, then one pole will approach the origin and the other pole will approach minus infinity. So geometrically speaking, now you have an idea of how to interpret the natural frequency and the damping ratio. So you can think about the natural frequency as the distance from the origin, at least for zeta that is between 0 and 1. Omega n is the distance between the origin. And again, if we're always with the damping ratio between 0 and 1, you can think about the damping ratio as to determine the position of the poles along the semicircle of radius omega n. So the smaller the damping ratio, the closer we are to the imaginary axis. And then as we increase the damping ratio, we are moving towards the real axis. So here I just drew again another S-plane. So starting from zeta equals 0, as we increase zeta, we're moving on a semicircle towards the real axis. So on the semicircle, we have the zeta between 0 and 1. And then we crash on the real axis for zeta equals 1. And we'll see it later, but when you have two poles that crash on the real axis, this point, it's going to be a double point, and is usually known as the break-in point, because you're breaking into the real axis at this point. If we were going the other way, the point will be known as the break-away point. But we're going to take a look at that concept later on, and in particular in week number 5. Anyway, going back to the description, as we increase even more the damping ratio, then we go away from the breaking point, moving to the left and to the right of the breaking point. Another very useful thing that you should remember is the angle, this angle here, which we're going to call theta. So it's the angle between the negative real line and the arrow that connects the origin to your pole. Let's say that we have a pole over here. So this angle theta is equal to r cosine of zeta. So if you have the damping ratio, you can calculate the angle. If the damping ratio was 0, then r cosine of 0 is 90 degrees. And that makes sense because if this angle is 90 degrees, the pole would be exactly on the imaginary axis. And for poles on the imaginary axis, we are on the undamped case, that is, the angle is equal to 90 degrees. It checks. Okay. Now, the next thing that I want to take a look at is the response, that is the output. So whenever I talk about the response, this is equivalent to talking about the output for a second order system to a couple of inputs. So we're going to consider the impulsive input. And recall that the impulsive input in the time domain is equal to the Dirac function, or in the S domain, that is simply equal to 1. And then we're going to take a look at the response of a second order system to a step input. And the step input in the time domain is equal to the unitary constant function. You can also, once again, think about it as equal to 1. Or in the S domain, the step input is equal to 1 over S. That is the unitary step input. Okay, we're going to analyze the impulsive input, and then I'm not going to cover step by step the response for the step input, but I've included in my notes all the steps that you would need. So feel free to go over them. All right, so if we have an impulsive input, the output being the transfer function times the input, well, but the impulsive input is equal to 1. So the output is simply equal to the transfer function of the system itself. So in this case, since we're considering a second order system, the output is going to be equal to g of s, that is the second order transfer function that we saw earlier. That is omega n squared over s squared plus 2 zeta omega n s plus omega n squared. How do we proceed in order to find the output? Well, if we want to work in the S domain, that's it. That's the output. But of course, we want to visualize the output, we want to visualize the function in the time domain. So we have to go back and remember the things that we need to do. We have to factorize the denominator, perform the partial fraction expansion, and finally perform the inverse Laplace transform in order to get back to the time domain. So we have to do exactly this. The first thing being, we need to factorize the denominator into its two poles. Oops, equal to. And what are the poles? Well, we've just computed them a few minutes earlier. So it depends on the case or the value of the damping ratio. We can have the undamped case, damped, that is without damping, the underdamped, the critically damped, and the overdamped. All right, so this is pretty much going to be a review of what we already know in terms of maths, but it's always a good exercise. All right, so for the undamped case, y of s is omega n squared over s squared plus omega n squared. Now, instead of performing the partial fraction expansion and do, sort of taking the long route here, we can recognize right away that we already have the inverse Laplace transform for this function. If you take a look at the tables, this is simply equal to omega n times sine of omega n t. So the function in the time domain is a harmonic function. And so if we plot this function, well, the amplitude is given by omega n. So we have the amplitude equal to omega n, but omega n also represents the frequency of this function. Or if you prefer considering the period is 2 pi over the frequency of oscillation. And so the period increases as the natural frequency increases, and the other way around, the period decreases as the natural frequency increases. Now, another question that we might ask ourselves is, can we apply the final value theorem in this case? Well, the poles of the functions are plus or minus I omega n. So the real part is equal to 0. It's not negative. And therefore, the final value theorem cannot be applied. And this makes sense because you see the function is a harmonic function. It oscillates forever, so it doesn't really have a defined steady state value or final value. It will always oscillate between plus and minus omega n. All right. Just before moving on to the underdamped case, you can think about as, for a real life example, just imagine a pendulum. If you move a pendulum from its vertical equilibrium, and if you were to neglect all the air drag and viscous friction forces at the pivot point, then this pendulum would just oscillate forever between, let's say, minus alpha and plus alpha. So this would be the undamped case. Without any drag or friction, then the pendulum would just oscillate between plus and minus alpha. In this case, it would be plus and minus omega n. All right, now let's complicate things a little bit more by taking the underdamped case. So the output is always equal to the transfer function, but now we retain the damping ratio because that is non-zero. So in this case, we do have to perform the partial fraction expansion. And so we need to find the two coefficients, A and B. In this case, P1 and P2, we already know them. And in this case, I'm going to take P1 equals to minus zeta omega n minus, and then P2 is going to be the one with the plus. As long as you're consistent, it doesn't really matter which one is which. Now, before proceeding, can we apply the final value theorem? Well, let's take a look at the poles of the function. The poles have real part that is negative. Therefore, the final value theorem is indeed applicable. And we are already able to, even before going back to the time domain, we're already able to find such final value by taking the limit for s that goes to 0 of s y of s. And I've already given you here the answer, but you can do it pretty quickly. Let's do it together. So this is equal to omega n squared times s over our denominator. All right, so if s goes to 0, then we have this goes to 0, this goes to 0, and the numerator goes to 0. So we have 0 over something that is non-zero. Therefore, the final value is equal to 0, as predicted. All right, but now if we want the long version of the output, we have to perform the partial fraction expansion and the Laplace inverse transform. So let's do that. So now we need to find a and b. We proceed as usual. We have a times s minus p2 plus b times s minus p1, and this has to be equal to omega n squared. We can rearrange things, so we have s times a plus b minus a p2 minus b p1 equals always to omega n squared. Now we can equate the coefficients of power-like terms. So we have that a plus b has to be equal to 0 because the coefficient of s on the left-hand side is equal to a plus b, but on the right-hand side, we don't have any s term. So a plus b has to be equal to 0. That is, b has to be equal to minus a. And what about the constant term? We have minus a p2 minus b p1 has to be equal to omega n squared. So we have minus a p2 plus a p1 using the first equation has to be equal to omega n squared. Therefore, a is equal to omega n squared over p1 minus p2, and b is the opposite. Now, what is p1 minus p2? Well, we have p1 and p2 defined up here. So p1 minus p2 is minus sigma omega n minus I omega n square root of 1 minus sigma squared. And then minus p2, we have minus zeta omega n, therefore plus zeta omega n minus I omega n times square root of 1 minus zeta squared. So this term and this terms cancel out, and we're left with minus 2I omega n square root of 1 minus zeta squared. So we can rewrite a and b without having to carry p1 and p2. So a is equal to I omega n over 2 square root of 1 minus zeta squared, and b is just the opposite of it. Okay, so now we're ready to perform the Laplace inverse transform. So let me rewrite y of s. So we have a times 1 over s minus p1 minus I omega n, that is b. Okay, so this is nothing new. We have y of t, the coefficient remains the same. And this fraction is transformed into e to the power of p1t. Same thing for the second term. We have e to the power of p2t. Now we're almost done. Now we have to substitute p1 and p2 at the exponential here. So we're going to do that. Then I promise this is the last long derivation for today's lecture. but it's important that you're able to do these things because most of the times, if you can derive things symbolically, then you can just plug in the numbers at the very last step. So it's always good to know how to manipulate equations. All right, with that being said, I'll just go ahead and write. All right, I can collect a common factor. And so we are left with e to the power of minus I omega n square root of 1 minus zeta squared times t minus e to the power of I omega n, same thing, just with the plus. Now, to make things a little bit easier, we're going to take omega n square root of 1 minus zeta squared, which is both here and here, and we're going to call this omega r, and this is known as the natural damped frequency. So omega r is equal to omega n times a factor that depends on the damping ratio zeta. And this is the natural frequency of the system, omega r, when the system is damped. So now what we're going to do, well, not only are we going to substitute omega r to make things a little bit easier, but we're also going to apply the Euler's formula. And remember that Euler's formula tells us that e to the power of ix is equal to cosine of x plus I sine of x. And once again, we're going to do that because we don't want to have imaginary parts in our equation that should be real. All right, so the first term is actually cosine of omega rt minus I sine of omega rt. And then we have minus cosine of omega rt minus I sine of omega rt. Cosine goes away with minus cosine, so we're left with minus 2I sine of omega rt. Now, if we multiply I with minus I, we're left with plus 1. And so we can write it all the way here. Y of t is equal to omega n over square root of 1 minus zeta squared times e to the power of minus zeta omega n t times sine of omega r t, where once again omega r is the natural damped frequency equals to the natural frequency or natural undamped frequency times square root of 1 minus zeta squared. Okay, so finally, you see that this case was a little bit more complicated, just a little bit longer, but not necessarily more complicated. It's something that we've already seen last week. So if you take a look at this function, you'll see that this is a harmonic function, but is modulated by an exponentially decaying function. So if we were to plot these functions, of course, they would be, we would have to choose omega n and zeta, but let's say that we fixed omega n, then we can draw, for instance, here I drew two of them. So they are exponentially decaying function, harmonic function modulated by exponentially decaying function. That is, you can think about it as harmonic function whose amplitude decays exponentially. And if you were to choose a higher damping ratio, the period of this function would increase. In fact, for a fixed natural frequency, the period, which is 2 pi over omega r now, increases as zeta increases. Instead, if you were to look at the functions for a fixed damping ratio, then the period would increase as the natural frequency would decrease. Okay, so you can draw as many functions for any values of the damping ratio between 0 and 1. You have infinite values between 0 and 1. Now we have to study the critically damped case. That is, zeta is exactly equal to 1. Instead of doing the whole partial fraction expansion and Laplace inverse transform, we can use one trick here. We can take the limit for zeta that tends to 1 of y of t for the underdamped case. That is, for the function that we've just found, underdamped. But before doing that, let's once again take a look at the nature of the poles. In this case, the two poles coincide and they are both real and equal to minus omega n. So is the final value theorem applicable? Yes, because the poles are both real and negative. And so once again, final value theorem is applicable and the final value is equal to 0. But one thing that I forgot to mention, in the underdamped case, just wanted to verify that the final value was indeed 0. Well, if you were to extend these functions as time goes to infinity, their amplitude would just decay asymptotically to 0. So indeed, their final value would be equal to 0. Now what happened here? Okay. All right, so let's take the limit for zeta that tends to 1 of the function that we found earlier. You'll see that we cannot really substitute directly zeta equal 1 because this denominator will go to 0, driving the whole function to infinity, which does not really make sense. And in fact, you'll see that there's a trick we have to apply. As a matter of fact, if zeta were going to exactly, if it was equal to 1, then as I said, this denominator will go to 0, but also the sine function will go to 0. So technically here we have a 0 over 0, which is undetermined. However, we can use this trick here. If you remember your limits, we can rewrite this as sine of omega n square root of 1 minus zeta squared times t. And we want to have a denominator, at the denominator, the same argument of the sine. Omega n square root of 1 minus zeta squared times t. And so here, rearranging what we have and what we don't have, we're left with omega n times e to the power of minus zeta omega n t. We need omega n squared n times t. Okay, why did I do this? It's because the limit for x that goes to 0 of sine of x over x is equal to 1. So in this case, we have the limit for zeta that goes to 1, but this is indeed equivalent to having the limit of square root of 1 minus zeta squared going to 0. And so in this case, x is equal to omega n square root of 1 minus zeta squared times t. So this whole limit here just goes to 1 as zeta goes to 1, not 0. So we're indeed left with the fact that y of t is equal to omega n squared times e to the power of minus omega n t times t. We can rewrite it over here in the box. All right, so here we have a linear function that is composed with an asymptotically decaying function. So for small values of t, the linear function is predominant. That's why you have that it grows in the beginning, but then the exponentially decaying function takes precedence and drives the whole thing to 0, as we were expecting. So for the critically damped system, the output, that is the response to an impulsive input, starts increasing at first and then decreases exponentially towards 0. We never cross, in this case, we don't have an oscillation like in case number 2. You see that the output oscillates, so crosses an infinite amount of time the real axis. In this case, we don't have that. Now, for the overdamped case, I'm not going to go step by step because we treat this case exactly like the underdamped case. The only difference here is the nature of the poles. The poles here are both real numbers. They're not complex conjugates, so we don't really have to use the Euler's formula, transforming an exponential to the sum of sine and cosines. However, it still takes a little bit of steps, but I'm going to leave it blank for you. If you're interested in finding the steps, I'll just provide you with the final result. By the way, in the complete notes, you'll find all the steps. But before doing that, let's once again take a look at the possible applicability of the final value theorem. Is the final value theorem applicable? Well, the two poles, as we proved earlier, are both real and they're both negative. So the final value theorem indeed applies. And once again, the final value theorem of this output is equal to 0. So as I said, I'm just going to provide you with the final solution. So this is the actual output in the time domain for a second order system when we apply an impulsive input. So you see here we have two asymptotically, we have two exponential functions, 1 and 2. So one has this and one has this. And although it looks mathematically more complicated, but qualitatively, it kind of resembles the critically damped case. So we have a curve that starts increasing and then exponentially or asymptotically decreases towards 0. And here, of course, we can have multiple plots for multiple or for different values of the damping ratio zeta. As zeta increases, you have a general trend of the plots following this direction. So for larger values of the damping ratio, you have that the function takes more time to get to its final value, that is to 0. All right. Now there would be the case for the step input. So what we want to do is to repeat the same analysis, but now considering a slightly more aggressive input. The step input in the S domain is 1 over S. So the output being always equal to the transfer function times the input has now an extra pole because we have third order or third degree polynomial as denominator. So one pole is equal to 0 and the other two are the old P1 and P2. So here the analysis is obviously longer because you have 3 coefficients to determine A, B, and C. Once again, this is going to be a little bit too boring, and I'm just going to skip it in a sense that I'm going to just leave the steps, and you're free to, or I strongly recommend that you try at least to replicate the steps until here. And then here I haven't really differentiated between the 4 cases. So between underdamped, critically damped, undamped, and overdamped cases. So you can do that. Or you can follow the steps that I've written for you. But again, you don't have to remember them. And you can just consider the final value or the final result when it comes to the function in the time domain. So for the underdamped case, we have 1 minus something that looks similar to what we found earlier, that is an exponentially modulated harmonic function. Then for the undamped case, we have 1 minus a harmonic function, in this case cosine. Critically damped, something again slightly similar, but always with 1 minus. And for the overdamped, it's a slightly more complicated. If you want details on how I found the expression for the overdamped case, just email me and I'll give you the steps. However, what I want really to take a look at is the overall outputs for the 2 cases. So once again, let's consider the impulsive input. So what I did here is that I plotted several outputs, fixing one of the 2 parameters and varying the other one. I remind you that the 2 parameters that we're considering for second order systems are natural frequency, omega n, and damping ratio, zeta. So in this case, if we wanted to plot the impulse response for a second order system, I fixed a value for the natural frequency, in this case 0.9. I haven't written, but the frequency is always expressed in radians per second. And now you see that with different values for the damping ratio, you're going to find different plots. So for an undamped case, we have this light green curve. And as you see, that represents exactly a harmonic function that oscillates between plus or minus omega n. You see that it goes all the way to 0.9 for its local maximum to a local minimum of minus 0.9. 0.9 is exactly omega n. Then as soon as we increase the damping ratio to values that are above 0, but below 1. And here I'm talking about the following 3 plots. So cyan, blue, and magenta. You see that for these curves, they start oscillating about 0, and eventually they converge to 0. As soon as we hit zeta equal 1, then we don't have the oscillating nature of the plot anymore, because now, as I described earlier, we start going up, and then eventually we settle towards 0. If we increase further the damping ratio for higher values of 1, then we don't have as high as a peak, but it's going to take more time to decay to 0, as you can see from the curve in black. Now you can see things from another perspective. Now let's take a look at a fixed value of the damping ratio, 0.3, for instance. So we're really considering an underdamped system. And then as you increase the value of the natural frequency, so here we have a minimum of 0.5 up to a maximum of 1.5, you see that as you increase the natural frequency, you decrease the period, but you also increase the value of the first peak, and of course of the second one and the third one, but it's more evident when you're considering the first peak. If the natural frequency is higher, the peak is going to be higher, but then the oscillation is going to be it's going to have obviously a higher frequency. Now, when it comes to the step input, we can take a look at the step response. And once again, the first family of plots are for a fixed value of the natural frequency. And here we start by considering the undamped case, once again with the same color and the green curve. So it starts from 0 and it oscillates between 0 and 2. And it will do that indefinitely. So all the way to infinity. You cannot apply the final value theorem for this case. As soon as we increase the value for the damping ratio, in this case from 0.15 to 0.3 to 0.5, now we have that the first peak decreases, we have a higher period, and we have an oscillation about the value 1. You take a look here. This is 1. And eventually we're going to converge to 1. However, when we hit the critically damped case, and even if we increase the damping ratio above 1, then we do not cross the 1 line anymore. Take a look at this red line. It will asymptotically reach 1, but it will never cross it. Same thing if we consider this black line for the damping ratio equal 2. And finally, if we fix the damping ratio and we increase the natural frequency with the same values from 0.5 to 1.5, you see that, well, the value of the peak does not change. So the value of the peak will probably be only a function of the damping ratio. And it is actually, we will see that next time. But you see that the only thing that changes is how soon you reach the peak. So if you have a higher natural frequency, you'll reach the peak sooner. So we're going to talk about rise time. So since the value of reference is always y of t equals 1, let's say that if you have a higher natural frequency, you're going to cross the one line sooner rather than later, but you're always going to reach the same peak if the damping ratio is the same. Okay, just one last thing that I want you guys to notice is that you always want to think about the output as how well the system tries to copy the input. And what I mean is the following. So for an impulsive input, we have that in the time domain, impulsive input is just a line with an infinite height that applies only at t equals 0 plus, and then afterwards is 0. So the output ideally should look like the input. However, since we have a transfer function, you can think about the transfer function as a sort of an inertia. So the input is sort of the force, and the acceleration is the output. But of course, the acceleration will depend on the mass of the system. So you can think about the transfer function as the equivalent of the mass of the system. So see all these outputs, they would want to look like the input, but they don't really look like it. So the best that they can do is sort of oscillate and then eventually go to 0. It's a little bit more apparent when we take a look at the step response. So the input in this case is the step unit input. So let's visualize it on the plot. So the unitary step input is just a constant function of height equals 1. So the output, see, well, here we have a lot of oscillations, but eventually, except for the undamped case, they all reach 1. So it's trying to mimic, the system is trying to mimic the input, but it will never be able to be exactly like the input. The only way for the output to be exactly like the input would be if the transfer function of the system was exactly equal to 1.